Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 8 of flow of water through soils. So, in the previous lecture we have introduced the flow net concepts, and we also seen the flow through unconfined seepage and confined seepage conditions, and we also considered the flow through anisotropic material. In this lecture we will try to understand the flow of water through earthen dams with rock filters or a rock toe at the toe of the slope, and stability of some hydraulic structures against piping or heaving failure. So, in the previous class we understood the flow nets construction in anisotropic material, and we also solved some example problems by considering an anisotropic nature of the soil in horizontal and vertical directions. That means that we considered the permeability is non-equal in horizontal and vertical directions, and then we try to get a transformed section by plotting to the scale which is with the variation of kh and ky, kh, kx and ky, and we also then seen the seepage through embankment dams, which is an example for an unconfined seepage. So, for calculating the flow through embankment dams or earthen dams, we said that the seepage is basically depending upon the construction of that phreatic line. So, for that many solutions were put forwarded, like we have seen the Jupit's solution and Schaffernak solution, and we also seen the Casagrande solution. So, several solutions have been proposed for the determination of the quantity of seepage through a homogeneous earth dam. Jupit solution, which was the first one, and then Schaffernak, and then the consequent the graphic construction and the Casagrande's solution was discussed by us. Then the flow net construction in earthen dam, we said that first, once the phreatic line has been constructed and approximated as per the methodology suggested by Casagrande, then if H is the head loss which is occurring, suppose if the H is the head which is driving the flow, and this is the upstream side, and this is the toe of the slope, and this is the downstream side, then depending upon the number of equipotential drops, simply divide this into delta H's, several delta H's. But maybe if there are say n number of equipotential drops, and divide this total head by n. So, easy to construct flow net in case of a flow of water through an unconfined seepage conditions, that is example is earthen dams. So, in this case the draw phreatic line, since this is known to us by the constructions and methodologies which are discussed, and here we should note that AG is an equipotential line. Suppose if there is a tailwater level here, then this happens to be again equipotential line, and pressure head at any point on the phreatic line is 0, hence the difference of the total head at any two equipotential lines should be equal to the difference in elevation between where these equipotential lines intersect the phreatic line. So, as the pressure head on these points is 0 along the equipotential line, so the difference in the elevation between points where the equipotential lines intersect the phreatic line, that can be taken as potential drops. So, delta H is equal to H by ND, ND is the number of potential drops. So, draw the total headlines for the cross section of the dam. So, these are the headlines, what it is called from the cross section of the dam, and draw the flow net, and then the seepage is determined Q is equal to K into H, which is the head which is driving the flow, NF by ND. NF is the number of flow channels. So, in this case if you approximate, there are 2 flow channels a 2.5 number of flow channels are there. Then this is the direction of the flow, then they can be numbered in this direction. So such a way that this equipotential drops are number is ND. So with this method, this is for a homogeneous soil, homogeneous earthen dam which is constructed, and which we have discussed about the method for determining the quantity of seepage passing through the earthen dam. So in this another example like flow net construction of an earthen dam, where you have got a headwater level and tailwater level, the situation is slightly different from the previous case. Then how the phreatic line changes. Say for example, here you have got a cross section of a dam A, B, the cross section of a dam which is shown here like this, and which has got an upstream water level which is having a head of H1 and a downstream water level having a head of H2. So if you look into this upstream phase, which is the equipotential line with a head H1 at all points. So AB is an equipotential line with head H1, total head H1 at all points, and AE is a flow line. AE is a flow line. So if this boundary is assumed as an impervious boundary, then AE turns out to be a flow line. Then in this case, DE is happens to be a equipotential line with head H2. DE is if H2 is equal to 0, then this point, this particular level will come down here, but the case here in this case is that there is a downstream water level with the head H2. So in that case, the DE, which is the equipotential line with head H2, so at all points here the total head is represented as H2 now. So here in this case the pressure head is 0, so the whatever the elevations which are having for the relevant datum, that is referred as a total head here in this case. So this BC is an approximated flow line, phreatic line which is shown, which is nothing but a flow line. The upper boundary of a flow line in this case of an earthen dam. So if you come to this small stretch which is shown here, the CD, where you will see that it is neither flow line nor an equipotential line, because component of flow normal to the CD exists, and water flows freely down the surface of the slope. So if you look into here, component of flow down the slope is either flow line or an equipotential line, because there is a component of flow which occurs down the slope, and there is a flow also normal to the CD. So it is eligible from both the point of view as an equipotential line as well as a flow line. So this type of discrepancies do exist in small locations there, but many times what will happen is that it is required to get rid of to keep the phreatic line within the dam, either to provide some measures like chimney drains or rock tows. So let us look into this flow net construction for an earthen dam with upstream water level and a downstream water level. Let us consider on upstream side there is a head H1 and downstream side there is a head H2. So in this case, if you consider a homogeneous earthen dam which is having a permeability of the material which is isotropic and having a permeability K in both the directions, and if a point here and then this is the crest of the slope, and from here if this happens to be the cross section of a dam, then AB is nothing but an equipotential line with head H1, and DE is an equipotential line with head H2, and AE happens to be the flow line, and BC, which is nothing but the phreatic surface, where here an approximated phreatic surface has been shown here. So if you note that if this being equipotential line, these flow lines have to be started orthogonal to this equipotential line, and here also the condition which is there is that they have to meet this equipotential line at right angles. So this indicates that this orthogonality has to be maintained, and AE is nothing but a flow line, because along with that if that is treated as an impervious boundary, then AE has to be treated as a flow line. So as the flow cannot take place through across this AE, because being an impervious boundary, so then the AE happens to be the flow line. So if you look into this, and this is a first flow channel and second flow channel, and then this qualifies as a third flow channels. If you approximate, the number of flow channels works out to be around 2 or 2.8. So if AB here which is at all points on this particular line will be having a total head H1, which is nothing but as the pressure head being 0, that whatever the elevation it has got from the reference datum, that is actually referred as a total head. So, that H1 will be the total head on the upstream side. So, as the water flows from H1 with a head H1 to the downstream water level H2, so the head loss which is occurring over a length which is nothing but total head loss is nothing but H1 minus H2. So, here if you look into the small zone where the CD that happens to be a point where it qualifies both for a equipotential line as well as a flow line, because there is a flow which is occurring perpendicular to that particular portion. If you look into the zone very close to that has a flow perpendicular to its particular point zone very close to CD, and there is also a chance that the flow can take place downstream the slope. So, in that case it is actually neither flow line nor equipotential line. So, this type of discrepancies do exist within this particular in the small zones where where upstream water level and downstream particularly toe water level or a downstream water level exists. So, here if you see here this being a flow line, you can see that these equipotential drops which are drawn perpendicular here and here again the orthogonal to the flow line. So, if this happens to be H1 minus H2, then divided by this number of equipotential drops, we will get that delta H which is occurring, a drop which is occurring between two consecutive equipotential lines. So, here like this one determines here and then again determine the number of flow channels, number of potential drops, and then head which is causing the flow H1 minus H2, and by knowing the permeability one can calculate the seepage. Now, let us consider many situations to keep the flow line to keep the phreatic surface, particularly within the upper boundary of the phreatic surface within the earthen dam. Generally it is practiced to provide some rock filter or rock toe or some measures like chimney, the chimney drains have to be provided within the dam. So, by providing that, what happens is that these phreatic surface are restrained within the dam itself, so that they are not be subjecting to a failure like against piping or so. This can be seen through an example. If you consider a similar cross section of a dam, and this being impervious boundary, and if this happens to be the upstream water level H1 and this is the soil with which the embankment has been constructed, and this happens to be the downstream water level with H2. Many cases when the flow line originates there is a chance that where a piping failure or a which is called erosion can occur, which can create the danger for the stability of a structure. So, many cases, many situations it is required to keep this phreatic upper phreatic surface, that is this being phreatic surface, to keep this phreatic surface within the earthen dam itself. So, for that the measures which are generally adopted are some chimney drain which is provided, or some rock toe, or some rock filter at the toe of the dam. So, in such situations how these particular measures can be, can affect the flow net construction and how the flow can be calculated. And in another case, like how these filters can be designed, what are the the grain size requirement, the criteria, so that these filters will function. So let us look into these embankments with some permeable filters. So in this case, in this particular slide, if you see, there is an embankment with a permeable filter which is resting here. So what you see is there is a rock toe, which is a rock filter which has been placed at the toe of the dam. So this particular being here, what happens is that this particular line is qualifies as an equipotential line with a zero head. Equipotential line with a zero head. If this happens to be the datum, then here the equipotential line with the zero head. So this is the cross section of the dam which we constructed. Now the difference is that from the previous slide and then now here, what we had is that now what we have is, now there is a permeable filter exists at the toe of the dam. So H is the head which is on the upstream side now. So by using the Casagrande's approximation, this 0.3 times delta, where delta is the distance from this upstream point A to this point where this head meets, that is the horizontal distance delta. So this point here is approximated from here as a 0.3 delta. So this particular portion is called as a basic parabola. So when this qualifies as an equipotential line, what happens is that this will be something like again this upper phreatic surface, that is the phreatic line now. So where here the phreatic line meets this equipotential line with a zero head orthogonally. If you look into this, these are the approximately shown as an orthogonal that is around right angles. So here the second flow line, you see that this one meets this particular point orthogonally, and again here which is approximately shown here is again meets orthogonally. So if this happens to be the Z and this happens to be X here, then the directrix which is going to be there here, and these determination of P and other from the basic properties of the parabola we have discussed in the previous class. So this particular case with the rock toe filter happens to be beta is equal to 180, because previously when there is a downstream case where beta has got certain angle. Now in this case the toe filter is existing with at the toe horizontally. In that case beta is equal to 180 degrees, and then the delta L by L plus delta L, that is at the downstream end. If you connect it to the previous lecture, the Casagrande's solution, the delta L by L plus delta L is equal to 0. So which is the case which is representing that particular properties here and properties of the parabola. And now in this case, if you look into it, the H is being the head loss. So delta H which is the any equipotential, the drop between the two consecutive equipotential lines. So in this case also again the procedure is simple, because this qualifies as a flow line, and immediately here if here there is again a discrepancy there where particularly it starts as a equipotential line. So so here number of flow channels, that is channel 1, channel 2 and then channel 3. So number of flow channels 3, and then equipotential drops. By estimating the number of flow channels and the number of equipotential drops, one can determine the quantity of seepage with the rock toe filter. So the basic merit of this particular solution is that it keeps the phreatic surface within the dam, so it prevents endangering the performance of a structure from against piping or heaving failure at the downstream level. How this filter can be designed, then before looking into different aspects. So when a seepage water flows from a soil with relatively fine grains to coarser material, that means that if a soil, if water which is actually flowing from fine grained soil to the coarser material, there is a danger that the fine soil particles may wash away into the coarser particles. So when the fine soil material wash away into the coarser particles, then there is a situation that clogging can take place. With that, there will be hydraulic pressures build up will take place, and again it endangers the performance of a structure. So, such a situation can be prevented by use of a filter or a protective filter between the two soils. Nowadays, previously it is a practice to use the sand being permeable, to use sand as a filter material, but nowadays with the modern development advanced in geotechnical engineering, there are some synthetic materials like geotextiles have been erupted and evolved, and they are being used widely for constructing this type of structures, and these materials being synthetic in nature, and they have got long life and got a enhanced performance compared to the conventional filters. So, when the seepage water flows from a soil with relatively fine grains to a coarser material, there is a danger that a fine soil particles may wash away into the coarser materials, and such situations can be prevented by use of a filter. So, the requirement or the situation where it demands is that basically to filter materials so that this particular phenomenon can be prevented. So, if you look into this typical flow net for an earthen dam with a rock toe. So, without filter at the toe, the seepage water would wash the fine soil grains into the toe and undermine the structure. So, suppose if there is no filter here, then what will happen is that seepage water would wash the fine soil grains into the toe and undermine the structure. So, here a particular slide here, a rock toe which is shown here, which is constructed with here, and here this particular zone which is constructed with a highly permeable material. So, which has got a criteria to be selected, that so that soil to be protected is not affected with particular in undermining the performance of a structure. So, here a cross section of an embankment dam has been shown on the toe side, and you are seeing a rock toe with a filter. So, the details which are shown here in this small window here, where soil to be protected, that is the soil which has been used in the embankment or earthen dam for construction, and the rock toe which is serving this purpose in preventing the undermining or a piping failure of the structure. So, this particular this thing for better factor of safety, and these measures have to be adopted. So, what are the criteria for designing this filter? For the proper selection of the filter material, there are two conditions to be fulfilled. So, for the proper selection of the filter material, there are two conditions to be fulfilled. The first criteria is the size of the voids in the filter material should be small enough to hold the large particles of the protected material in place. So, the material has to be selected such a way that the size of the voids in the filter material should be small enough to hold the larger particles of the protected material in place. So, if this material gets washed out of the filter material, then there is an endangering or the stability of the structure is in question. So, the size of the voids in the filter material should be small enough to hold the large particles of the protected materials in place. So, that is the criteria number 1. The criteria number 2 is the filter material should have a high permeability to prevent the buildup of large seepage forces and hydrostatic pressures in the filter. So, the second criteria being condition is that the material should have higher permeability, that is should have high permeability. So, it should be freely drainable, and to prevent, basically the requirement is that to prevent the buildup of the large seepage forces and hydrostatic pressures in these filters. So, if these hydrostatic pressures can build up, then there is a problem of again endangering the structure. So, the filter which is to be designed has to be followed with these two criteria which was set forwarded, and then the material has to be selected and designed, and then has to be implemented in the construction of dams with earthen dams or embankments, say for this particular purpose, if it is used, and can be constructed with this type of filters with properly selected materials. So, the criteria in this terms of like according to Bertram 1940, based on the experimental investigations, some criteria have been set forward for protective filters, and they are here the D15 of filter, the ratio of D15 of filter to D85 of soil should be less than or equal to 4 to 5. That is the criteria. This is to satisfy the criteria number 1, that is D15 of filter soil, ratio of D15 of filter soil to D85 of soil should be less than or equal to 4 to 5. And in order to fulfill the criteria 2, which is another criteria which has been set forward, is D15 of filter soil to the D15 of the soil, it should be ratio of this D15 of filter soil to D15 of soil should be greater than or equal to 4 to 5. So, by fulfilling these two, if the material has been selected such a way, then that qualifies as an ideal filter material, and then it serves the function like what has been desired by satisfying these two criteria which are discussed. So, here D15F is nothing but the size through which the 15% filter material will pass. So, D15F is nothing but the size through which the 15% of the filter material will pass. D15 soil means size through which 15% of soil to be protected will pass. So, here D15S means the size through which 15% of the soil to be protected will pass. And D15S, D85S is nothing but the size through which 85% of soil to be protected will pass. So, these are the definitions for the symbols which are used in these two sets of expressions, where the first one is being for the satisfying the criteria 1, D15 filter by D85 soil, then that ratio is S is nothing but the soil to be protected, F legend nothing but the filter material. So, D15F to D85S should be less than or equal to 4 to 5, that is required to be, that is to criteria number 1, and for satisfying the criteria number 2, D15 filter to D815 soil which should be greater than or equal to 4 to 5. So, this is a typical cross section of along with the flow net for an earthen dam with the chimney drain. So, this particular construction here is there is a toe filter at the bottom, and then there is a drain which is placed here. So, with this what happens is that the phreatic surface will be restricted and restrained within the central part of the dam itself, and these for the design there are methods which are to be arrived for arriving at the dimensions, and based on that, once arriving, then by using the methods which are discussed, one can construct the phreatic surface and the flow net, and then quantity of seepage can be calculated. So, here again the chimney drain is constructed with a particular type of selected material, and then we can have filter so that it serves the function. So, here in this case if you look into it, there are 1 and 2, so 2 flow channels which are there, and this qualifies as a flow line, and this particular boundary if it is treated as impervious, and this is particularly here this qualifies as an equipotential line with the head 0. So, here this particular portion again is qualified as equipotential line with head h, whatever it is here, small h, if it is if the small h is the head loss which is causing the flow, and that is considered here as h. And so, based on that, here these are the equipotential drops which are going to occur, and that is which is represented here delta h. In this case for these lines 1, 2, 3, 4, 5 equipotential drops which have been considered. So, ND will be equal to 5, and then NF which is approximated as say 2.5 or so, then in that case we can approximate as a that NF by ND, that particular ratio, and then by knowing the material K and by knowing the H which is there, we can again estimate the quantity of the seepage. So, having discussed now, then let us try to consider how to evaluate this factor of safety of these structures against piping or heaving failure. And while designing this particular phenomenon, and we said that when the flow takes place downward directions on the upstream side of a say particularly a row of sheet pile walls embedded in a soil, then when the flow is taking place, when the flow channel commences, there is a downward flow, but when it is erupting out, when it is coming towards the downstream side, there is a chance of a upward flow. So, we whenever we have an upward flow or a downward flow, in case of downward flow, we knew that because of the energy which is transferred to the grains, then what happens is the effective stresses increases. In case of a upward flow, then we discussed that effective stresses decreases. So, these decrease in effective stresses which are there on the downstream side of a structure can affect particularly this performance of any hydraulic structure. So, let us consider a cross section of a sheet pile wall
which is let us assume that this is H1, H2. So, this particular depth, which is referred as embedment depth of a sheet pile wall. So, this particular line, this is a cross section which is shown, and this is the impervious boundary. The impervious boundary which is shown here, the impervious boundary which is shown here. Then this particular line represents two-dimensional view of sheet pile wall. In this case, the first flow line creeps along the sheet pile wall. Second flow line erupts out like this, which are approximately drawn. So, here being a equipotential line, orthogonality has been maintained. So, this is the flow channel. If this being a flow line, so there will be these are the equipotential lines which are drawn like this. So, when the flow which is taking place like this, so here which is the downward flow which is taking place, and here upward flow. So, this particular place where here, suppose if this happens to be the head which is occurring here, the head loss occurring between these two equipotential lines happens to be delta H, and if this length happens to be say delta L, this length delta L can be obtained from the flow net construction, and this is delta L is nothing but the length of the flow, and delta H is nothing but which the head drop which is occurring between this equipotential line and this equipotential line, and here is a downward flow. So, as discussed here, the effective stress increases here, and here effective stress decreases. So, in the process here, what happens is that this particular gradient which exists here is defined as I exit is exit hydraulic gradient. Exit hydraulic gradient, which is nothing but delta H divided by delta L. This is one parameter. Then we also discussed that a critical hydraulic gradient, which is again discussed while discussing the flow of water through soils, and that we defined that when the head reaches the critical head by the length of that flow, that is actually treated as a critical hydraulic gradient, and we have said that it is can be related with the GS minus 1 by 1 plus E divided by gamma dash by gamma W. So, I exit, which is nothing but a delta H by delta L, and then critical gradient. By using these two, then we will try to get a factor of safety against this piping or heaving failure. So, here in this particular structure, this is being a typical flow channel is shown. There will be a number of flow lines, but this is the first flow line, and second flow line typically shown here, and the exit gradient is defined here, and this is the row of sheet pile walls. That means that perpendicular to this figure, per meter width of the figure, if you consider, there will be a row of sheet pile walls which ensures the leak proofness and then retains the water H1 with a head H1 on the upstream side, H2 on the downstream side. So, then the flow takes place with a head loss H1 minus H2 over a length here. So, the cross section, if it is given and if it is homogeneous, then if this being a soil, then this is how the procedure has to be done. But what we are being discussed is that two cases, that there is a chance that this entire layer can get uplifted, and that particular case will be discussed now. Then afterwards there is by using another method to evaluate the factor of safety against piping failure, that is based on this exit gradient method. So these two methods we will discuss shortly. So let us try to look into the failure due to piping for single row of sheet pile wall structure. So this is after Tarjagi 1922. So consider a cross section of sheet pile wall and assume that on the downstream side a wedge of soil or a prism of soil is subjected to some uplift. So here consider a cross section of a sheet pile wall which is embedded in a permeable layer, and D is the embedded depth, and this is an impermeable layer, and according to Tarjagi, this particular zone is referred as a possible failure zone. This particular zone, which is D of depth D and D by 2, that is embedded depth times that is 1 by 2 times the embedded depth, this particular zone is identified as a possible failure zone by the Tarjagi. So how to evaluate the failure due to piping for single row of sheet pile wall structure according to Tarjagi 1922. So by considering a soil prism of the on the downstream side, because that is what actually we have discussed it, that where the uplift flow can take place, upward flow can take place with an uplift pressure at the base of the prism. So a thickness that is per unit thickness, if it is considered a section of D into D by 2, that is the 2-dimensional plane area, and per meter width is subjected to an uplift which is existing at that particular portion. So using the flow net, the hydraulic uplift pressure can be determined. So if first let us look into this particular portion W, which is now W dash is equal to half gamma dash D square. W dash is equal to half gamma dash D square, that is nothing but the self weight of the soil which is being soil prism which is being subjected to an uplift. So here gamma dash is the submerged unit weight of soil, and D is nothing but the depth of the soil sheet pile wall which is embedded. So W dash is equal to half gamma dash D square, and the hydrostatic uplift pressure can be estimated by using U is equal to half gamma W D Hm. So here it is nothing but, suppose if points A and B are existing on the say at the tip of the sheet pile wall, say A, and at a distance D by 2 from the sheet pile wall, if it is say B, then the head at which is occurring at the head which is available, the total head which is available at A is HA, and the total head available at B is say HB. So in that case the average head which is HM or H average it is referred, is calculated by computing the total head HA and total head B. So that is given by Hm is equal to HA plus HB by 2. So with that now we can determine Hm. Once the Hm is known, at the base of the prism what is the uplift pressure which is exerted by this pore water pressure which is existing at that point, because as the flow taking place from upstream side there is a dissipation of pore water pressure which takes place, but whatever is existing at points A and B, based on that we calculate the total heads, and then that is used as a calculating the hydrostatic uplift pressure. So remember here the average hydraulic head is determined by calculating the total heads at the respective equipotential lines or the lines approximated to lines which are passing to that particular zone. So here by doing that, this is the prism of soil, the distribution which is there with HA and HB, and which is approximated as U, which is nothing but with an HA or HM, which is given as HA plus HB by 2. With that now U can be determined as 1 by 2 times gamma W D into HM. So in this slide what we said is that now there is a sulfate of the soil which is existing is W dash is equal to half gamma dash D square, and then on the same section at the base it is subjected to an uplift force U. So by considering the vertical equilibrium or a factor of safety which is nothing but now the weight which is ratio W dash by U. If you consider that, if that has got say adequate factor of safety, then we can say that it is safe against piping failure. So now the extending whatever we have discussed